has now occurred to me that probably I know Zhenya longer than anybody else at this conference, and practically than and almost anybody in the world. We lived practically in the same house. Our fathers worked in the same institution. We went to the same school and had the same teachers. And even now, whether we work on the same problems, it depends from which distance you look. Most people would say that yes. Zhenya kind of worked in group theory. I started in algebras, but then I moved to groups, and Zhenya moved to Lie algebras. I will talk on growth of everything. Growth of infinite groups, infinite dimensional algebras, monoids, languages, anything that is infinite and grows. Okay. So let us start with groups. That's the most classical part of the subject. So suppose that a group is finitely generated. It is generated by m elements, and we consider the subset which consists of products of generators and their inverses of length up to n. If you look at the Kelly graph, which is a metric space, it is just a ball of radius n with the center at the identity element. These balls grow, and their union is the whole group. And we can discuss orders of these finite sets, that is an increasing sequence. We can discuss how fast it grows. Unfortunately, this sequence depends on the choice of generators. Therefore, we need to define some equivalence. Let's consider two functions f and g that are both defined on natural numbers, two increasing functions. We say that the function f is asymptotically less or equal to the function g if there exists a constant such that we always have this inequality for any n. If f is asymptotically less or equal to g, and g is asymptotically less or equal to f, then we say that they are asymptotically equivalent. Any two polynomials of the same degree are asymptotically equivalent, and any two exponential functions are asymptotically equivalent. So this is a very rough equivalence. But if we consider two finite generating sets in a group G, and they both define some growth functions, then these growth functions are asymptotically equivalent. So growth of a group is not a function, it's a class of equivalence. Motivation, this concept was introduced by Schwarz, Efrimovich, and Milner. Motivation comes from geometry. If you have a Riemannian manifold and fix a point, and you consider this group theoretic growth of the fundamental group, and on the other hand, you consider the growth of volumes of balls centered at this point, then these two types of growth are asymptotically equivalent. That's where it came from. And another reason to consider growth of groups was just an attempt to compare infinite groups. If you have two finite groups, you can say that one of them probably has more elements than the other one. But if we have two countable groups, we can compare which one grows faster. And the same concept can be defined for monoids, semigroups. It's all the same, but no inverses. And even for hereditary languages, I want to say more about hereditary languages. Suppose that we have an alphabet of M letters, and we have a certain set of bad, prohibited words.
Good idea.
Yes. Then we consider all words that do not contain bad words as subwords. And that is the language. We add 0, and this is a monoid with 0. It is just defined by these relations. Stepin and Grigorchuk had some interesting explicit formulas for the growth of these languages. Growth is just the number of words of given lengths, or lengths less or equal than n. I will say more about growth of languages later. Now let's talk about algebras. Let F be a field, and we consider a finitely generated algebra, well, generated by a finite dimensional subspace V. Let Vn be the span of all products of all words of length in elements, all products of elements from V of length up to n, with all possible brackets. I never said that the algebra A is associative. Anyway, this is a finite dimensional space, and these finite dimensional spaces grow, and their union is the whole algebra. And this is an increasing sequence, and we can discuss how fast it grows. I said that, well, we could consider this concept for non-associative algebras, but today we will discuss only associative algebras. If this function has polynomial upper bound, then the infimum of degrees of all these polynomials is the so-called Gelfand-Kirillov dimension of the algebra A. And by the way, again, we discuss these functions up to asymptotic equivalence, because we may choose another finite dimensional generating space. Gelfand and Kirillov just needed to prove that two countable dimensional algebras are not isomorphic, and they introduced this invariant. In 1968, John Milner published a very influential survey on growth of groups in Mathematics Monthly, which is a journal for undergraduate students. In this survey, he formulated two problems. First, is it true that a group has polynomially bounded growth if and only if it has an nilpotent subgroup of finite index? At that time, it was known that a finitely generated nilpotent group has polynomial growth, and for subgroups of finite index, no, still polynomial. And another problem, do there exist groups with intermediate growth, that is, groups that grow faster than any polynomial and slower than any exponential? Both problems were solved in early 80s. In 1980, Gromov proved that yes, indeed, a group has polynomially bounded growth if and only if it has an nilpotent subgroup of finite index. I want to say a few words about the proof, because though it was a very important result, but probably the proof was even more important. It is the beginning of geometric group theory as we know it. In 1962, Jacques Tits proved Tits' alternative, a finitely generated linear group, is either virtually solvable or contains an abelian free subgroup and therefore has exponential growth. So in particular, and for solvable groups, the answer, it was known that there are no intermediate growths. It's the result of Joe Wolf. So Tits answered Gromov's question for linear groups. Now, Gromov's idea. Let this G be a group. we consider it as a metric space. Say we consider Cayley graph, and every connected graph is a metric space. And this is a helicopter. Well, suppose that helicopter goes up, and then group is a discrete metric space. But as it goes up, points become closer and closer to each other. They look closer and closer. And that defines a certain limit. He did it formally. And that limit, if the growth is polynomially bounded, it turns out to be a manifold. So the group now acts on the manifold. And then using the solution of Hilbert's fifth problem, he proved that this manifold is, well, it has all smooth properties, and therefore the group that acts on it is a linear, has a homomorphism to a linear group, and used its result. So the proof was based on the solution of Hilbert's fifth problem, which is longer than the proof of Gromov's theorem. It was a bit unsatisfactory. And then Bruce Kleiner invented a new proof. A new proof means that it did not rely on the solution of Hilbert's fifth problem. And the proof was based on works of Nguyen Mock on spaces of harmonic functions. Well, in 1983, Grigorchuk also solved the second problem. Indeed, he proved that there exist groups of intermediate growth. And his group was a group of automorphism of a rooted tree. Well, now the first question, what is the growth of the Grigorchuk group? He only proved certain inequalities, which showed that it was intermediate. And the answer is interesting. Let's consider this cubic equation. It has a root, well, which is approximately equal to this number. And let us take the logarithm of 2 with the basis of this root. It's approximately equal to this. The theorem, which was due to Bartholdi, its upper bound, and recent work of Erschler and Zheng, its lower bound. The growth of the Grigorchuk group is this. And if you look at the paper of Erschler and Zheng, you won't believe that this is a paper in group theory. It's random walks on these groups. It's a probability. Now, the basic question for all these objects, groups, algebras, monoids, and so on, languages, which functions appear as growth functions, of course, up to asymptotic equivalence, of groups, algebras, monoids, and so on. It is clear that not all functions. Well, a growth function is an increasing function. A growth function is also submultiplicative, because if you have a word of length m plus n, it is a product of the word of length m times a word of length n, and therefore you have this inequality. Well, there was movement in the direction of positive solution of this. Well, the natural conjecture was, is it true that these two conditions are, so they are necessary, but is it true that they are also sufficient? So any function which is increasing and submultiplicative is equivalent to, asymptotically equivalent to a growth function of a group. Bartholdi and Erschler proved that if the function lies between Grigorchuk group and exponential and is sufficiently regular, which means that there are additional conditions that I don't want to formulate. So if it is sufficiently regular, then yes, this function is asymptotically equivalent to the growth function of a group. And in all these questions, how do you prove it? You have to construct some examples of groups. And they constructed examples that were kind of close to Grigorchuk group. I want to say that in algebras, new examples of algebras of sub-exponential intermediate growth appeared, but in groups, practically all examples are very close to Grigorchuk group. Of course, Nekrashevich constructed a simple group which was periodic and had intermediate growth. But again, it was a group of isometries of some metric space that looked sort of close to a tree. Well, and Grigorchuk has a conjecture that there are no growth functions in this segment, that if between polynomials and e to the power square root of n. And he proved it for residually p groups. It was not trivial. Let's talk about what is known about Gelfand-Kirillov dimension. Of course, all finite dimensional algebras have Gelfand-Kirillov dimension 0. And there is nothing between 0 and 1, because you remember we considered this increasing chain of finite dimensional subspaces. If there is stabilization at one point, then that's it. This is the whole group, whole associative algebra, and it is finite dimensional. So at each point it increases at least by 1, and it already gives you linear growth. There is nothing between 0 and 1. Then there is also nothing between 1 and 2. It's a less trivial result. It was first time proved by Hedlund and Morse in a different language in 1938, and then by George Bergman in 1970. So now it is known as Bergman gap. I remember S.T. Yao once wrote about the paper, a new proof of some of his students of some old result. He said he wrote that yes, it was done before. Well, and then starting with 2, any number can be Gelfand-Kirillov dimension of some algebra. Bartoldi and Smoktunovich proved that if gamma is an increasing submultiplicative function, that there is a growth function that is sort of close to it. If the function gamma is polynomial, then you may say it's not very close. But if it is super polynomial, then multiplication by n squared does not change much. In general, there are more algebras of intermediate growth than groups. Marta Smith proved that if L is a Lie algebra of sub-exponential growth, then the universal enveloping algebra also has sub-exponential growth. And that creates a big class of algebras of intermediate growth. For example, consider algebra of polynomials over finite dimensional Lie algebra. It is of sub-exponential, so of linear growth. Therefore, the universal enveloping algebra is sub-exponential, but this algebra is infinite dimensional. Therefore, it's super polynomial. Well, now let us go back to the description. I will make an attempt of description of all growth functions of algebras, monoids, and hereditary languages. For groups, it is still not known. So let f of n be an increasing function, and let us consider its discrete derivative. The following theorem is joined with Jason Bell. It's in 21. Suppose that the function, is big enough, at least linear, submultiplicative, and another inequality. You may ask, why doesn't it follow from submultiplicativity? I never said that the function f of n is increasing. Well, every growth function satisfies these conditions, and if the function f satisfies these conditions, then there is a hereditary language which is asymptotically equivalent, whose growth is asymptotically equivalent to this function. So this is a description of growth functions of algebras, monoids, and languages up to asymptotic equivalence. Well, so the point is that the condition of submultiplicativity was imposed not on the function f, but on the derivative. And submultiplicativity for derivatives is stronger than submultiplicativity for the function. We all remember from calculus of the first year that inequalities can be integrated, but not differentiated. Well, so after this theorem, Beery-Greenfeld immediately constructed, it's an exercise for calculus of the first year, a function whose derivative is submultiplicative, but the function is not. So the original conjecture is wrong. Well, now some remarks. These conditions that I formulated are not asymptotically invariant. Well, we know how to make them asymptotically invariant. It's a bit more technical. And the second remark. How do we prove the existence of these growth functions? We have to construct languages. We have to construct these systems of bad words. But in these languages that we constructed, there was a lot of trash, words that are not expandable to infinity. So it was natural to ask, what if we are interested, if we count only infinitely extendable words? Then it would imply that the second derivative is non-negative. And then the story goes this way. I gave a talk on this subject at the joint Chinese-Brazilian conference. And there was, just a second. There was Carlos Gustavo Moreira in the audience. He is more known as Gugu. And he's a very well-known person in dynamical systems, one of the top people. And he listened, and then he gave me his preprints, and they are all on the same subject. And now the subject is following. It's one of the oldest subjects in combinatorics and symbolic dynamics. Suppose we have a finite alphabet, and we consider the set of infinite words. The complexity function is the number of words of length n. This is the analog of derivative. Or you could ask about the number of words of length up to n. Or you could ask about complexity functions of formal languages, the number of words of length n, which is virtually the same thing. The smallest possible complexity of a non-periodic sequence is n plus 1. It's like it corresponds to algebras of Gelfand-Kirillov dimension 2, Bergman gap. Now, in this case, the infinite sequence is called Sturmian sequence. And for example, it's connected to many things. If you consider a number and its q-adic expansion, it's an infinite word in the alphabet of q elements. If this infinite word is Sturmian, so has complexity n plus 1, then the number is transcendental. Well, And it has been an open problem since 30s. What are possible complexity functions? Of course, I should say that, and even they asked what type of growth do they have? It is in groups, it's very natural to consider growth functions up to asymptotic equivalence. For complexity, we are interested in precise functions, but the first approximation up to asymptotic equivalence is also interesting. It gives an idea about possible types of growth. And after our work with Jason, it became clear where to move. Now, this is a very recent theorem joined with Gugu and Beery Greenfield, just proved. Well, we started to work on it together, but the last step was just incredible combinatorial equilibristics of Gugu. You know, he's a former gold medalist in International Olympiad, and I learned to appreciate them after this joint work. If the function again satisfies these two conditions, and it is increasing, which we did not impose before, then it is asymptotically equivalent to complexity function. And I want to formulate another result. Suppose we have a hereditary language, and we assume that the set of bad words kind of is minimal, that bad words don't contain another bad words. Otherwise, what's the point of keeping it on the list? So a letter is called regular if no bad word starts with it and no bad word finishes with it. Well, if there is a regular letter, then of course it is the language is extendable. You can just write this letter at the end infinitely many times. You will never get zero. So it is a more narrow class of languages, and the theorem, the same group, same group of people. Suppose that, again, the function is big enough, submultiplicative, and this function grows. It is stronger than f grows. Then it is asymptotically equivalent to complexity of a language with a regular letter. And here, the key is a certain construction of a rest product of languages. I won't go into details, but it looks very much like Riesz product of groups. And this is a Riesz product of languages that produces all these complexity functions. Okay, now let's talk about nil algebra. An associative algebra is called nil if an arbitrary element is nilpotent. In 41, Alexander Courage decided to formulate a problem which was an analog of Burnside problem for algebras. Suppose you have a finitely generated associative algebra and it is nil. Is it finite dimensional and nilpotent? Pure analog. In fact, Golat and Golat, well, based on the joint work with Shafarevich, first constructed counterexamples to Courage problem, and then he used them to construct counterexamples to Burnside problem. Now another question. Does there exist a counterexample of polynomially bounded growth? If you ask the same question for Burnside's problem, then the answer will be positive. If a group has polynomially bounded growth, then by Gromov's theorem, it is virtually nilpotent. If it is also torsion, then it is finite. But for algebras, no. Lenagan and Agatas Maktanovich in 2007 constructed examples of finitely generated nil algebras of polynomial growth, but only over countable fields. Well, the original Golod's examples were also first constructed over countable fields, then they were extended to uncountable fields, and that did not happen so far in the case of algebras. Later, Lenagan, Smoktanovich, and then my student Alex Young constructed an algebra with Gelfand-Kirillov dimension lying between 2 and 3. So the growth was between quadratic and cubic. And then Jason Bell and Alex Young also proved that over an arbitrary field and arbitrary superpolynomial function, there exists a finitely generated nil algebra with this growth. Well, I should say that it is still not known if there exists a finitely generated nil algebra of infinite dimensional of polynomial growth over an uncountable field. Well, so what are possible growth functions of nil algebras? Well, I conjecture that all growth functions, well, starting with n squared, can be realized as growth functions of nil algebras, which means that there are just many nil algebras. And all theorems that I will formulate now are joined with Beery-Greenfield. They appeared last year. So if the field is countable, then and P of n is the growth function of the Lenagan-Smoktanovich-Young algebra, it lies here. And let f of n be an arbitrary increasing submultiplicative function, then this product is asymptotically equivalent to a growth function of a finitely generated nil algebra. Again, if f of n is superpolynomial, then that's a small change. Over arbitrary fields, the result is somewhat weaker. This. If delta is an increasing function and omega is superpolynomial function, then you always can construct a growth function of a nil algebra that lies in this segment. Now, another strange behaving growth functions, oscillating growth. First, Kasabov and Igor Pak constructed groups whose growth functions were oscillating. They were infinitely often smaller than this and infinitely often bigger than any subexponential function. Just choose it bigger than this. And the example was again somewhat close to Grigorchuk example, certain groups of automorphisms of trees. Later, Petrogradsky constructed analogs of, he constructed restricted Lie algebras over fields of prime characteristics that were nil and had growth functions that was oscillating. They were Lie algebras, but they were analogs of Grigorchuk group. In that paper with Beery-Greenfield, we constructed associative nil algebras of a field of arbitrary characteristic with oscillating growth function. So in particular, you can get a Lie algebra from it, of zero characteristic with oscillating growth function. Again, over countable fields, the result is somewhat better, infinitely many times less than this, infinitely many times more than any function, any subexponential function. You can ask more precise question, not just infinitely many, but you can ask both sets to have non-zero measure. Well, over arbitrary fields, The result is somewhat worse, but again, oscillation. And there are even finitely generated domains with oscillating growth functions. This theorem about domains, we used it to answer another question. If you consider tensor product of two algebras, then the growth function of the tensor product, of course, is less or equal than the product of growth functions. So hence, the Gelfand-Kirillov dimension of the tensor product is less or equal than the sum of Gelfand-Kirillov dimensions. Bill Warfield showed that this inequality may be strict. And he asked if it can be strict in a very strong form. That was his question. And Krempa and Dokninsky proved that constructed examples showing that yes, indeed, it can be strict in this strong form. But the examples, unfortunately, last page didn't come here. The examples were contained very big radicals, and the proof was a play with those radicals. And they asked, and then Krause and Lanagan asked also, if there are examples that have zero radicals. And from our result on oscillating functions of domains, we constructed these examples. Indeed, they could have zero radicals. Well, 39 minutes. Thank you.